Well, my name is Sanjeev and currently I'm an instructor at Re-Level by an academy. So today we are going to discuss a very interesting problem named LS burning tree. So before moving forward, let me tell you what you can expect from this particular video. So in this video, we are going to discuss firstly your problem statement, then we will see the input output format, then we will see how you can solve this particular problem, what should be your approach, and then we will discuss the implementation and code of this particular problem along with the time complexity. So let's just move forward and let's see what the problem statement says. Here you can see that problem statement is Alice has a connected tree having n nodes numbered through 1 to n. So from this you can get at least an idea that problem is about the tree data structure. Nodes of the tree are connected through n minus 1 bidirectional edges. Okay, so all the edges are connected through each other, and for n nodes there are n minus 1 bidirectional edges. So from A to so you can go from A to B as well as B to A. It is known that the tree the tree is rooted at node 1. In Alice's city, the fire is gravitational. That is, if you fire up a node X in the tree, then it will burn all the nodes that are present in the subtree of X, including the node X. Okay? So you will be given Q queries in ith query asked you to fire up the tree exactly at one node in such a way that it burns nodes numbered AI and BI. But the constant But the constraint is that you have to fire up the tree in such a way that it burns the minimum possible number of nodes. For every query, print the minimum possible number of nodes that would be burned in your fire. So there are some points to note. First is the tree is connected, which means always exist at least one way in which you can fire up the tree in such a way that node A and node B would be burning. Second point is each query is independent of the other. That is, after each query, tree would be restored to its initial position. Now let's check out the constraints. Constraint says that your number of test cases would be 1 to 10 raised to the power 3. Value of your number of nodes and queries can be up to 10 raised to the power 5. Your numbers, that is, the node numbers can be up to n. So let's just move forward and let's see the input and output format. So in input and output format, first line would be your single integer, that would be the number of test cases. Then after that, first line of each test case contains two integers n and q, that how many nodes would be there as well as how many queries would be there. Next of the n minus 1 lines contains two space separated integers xi and yi, that would show that if there is an edge between x1 and y1. Next is each of the queue lines contains two space separated integers ai and bi, that is the nodes that we have to burn in ith query. So the sum of n and q
7 बजे
over all the test cases would never exceed 2 raised to the power 2 into 10 raised to the power 5. And your output format would be for each test case, you would be outputting q lines that would be equal to number of queries, and for ith line you would print the minimum possible number of nodes that would burn in your fire in ith query. Now let's see some sample input. So for this particular sample input, we have this sample output. Now let's make a tree for this particular sample input. Here I have copy pasted the sample input as well as sample output for your reference. Now let's see what this particular sample test case says. So there would be first line which is showing you number of test cases. It is 1. So there would be only one test case. Now the next line is showing your number of nodes as well as number of queries. So here you can see the number of nodes is equals to 5 and number of queries would be equals to 2. After that you would get, so as we know, for n edges, for n nodes, there would be n minus 1 edges, right, for a tree. So as there were 5 nodes, now we can say there would be 4 edges, and here we can check which all 4 edges are they. So first is, let's draw the edges. So your first edge is between 2 and 1. So as we know, 1 would always be a root, and we have another node as 2. Then there is one another node. Then there is one another edge between 1 and 3. So let's make an edge between 1 and 3. Now there is one more edge between 5 and 3. So let's make one more edge between 5 and 3. After that there is one more edge between 3 and 4. So there is one more edge between 3 and 4. Now you can see we are having all the 5 nodes which are connected through 4 edges. So we have covered all the 4 edges. Now after that there would be queries. So as we know, there would be 2 queries. So your first query is 4 and 5. So as you know what we need to do with queries. So here your A is equals to 4, your B is equals to 5. So we need to put fire at some particular point so that 4 and 5 would be covered in its subtree, right? And they will get burned. So let's say if we will put fire at root itself, so you can see all the nodes would get burned. 2, 5, 4, 3, right? Everything would get burned and we are done. But here you need to burn only minimum number of nodes possible, right? So to find minimum number of nodes, so to find the minimum number of nodes that we need to burn, to burn 4 and 5 also, what we will do is, instead of burning the whole tree, we will see where we can put fire so that 4 and 5 would be covered in that subtree. So here, if you want to burn 5 as well as you can burn 4, you can see in which subtree they occurs. So we will come to its ancestor, and you can see the ancestor of 4 and 5 is same, that is 3. So here, if I will put fire on 3 will get burned, as well as its subtree, that is 5 and 4 would also get burned, and we are done. A and B got burned. So for that, how many total nodes we needed? Here we needed total 3 nodes to burn, right? So for your first query, your answer should be 3, and we can see in output it is 3. Now your next query is, and for every query, your tree would get restored again. So here your tree will get restored again. Now for the next query, you are having A as 2 and B as 2, right? So now you have to burn only one node, that is 2, right? So A is also, A is 2 and B is also 2. So if you only need to burn node 2, there is no need to burn any other node to burn only 2, right? So we can directly just put fire on 2. In this particular case, to burn 2, you will need only to burn one node, and that is your answer, right? So guys, if basically you will see what we are doing, we are having two nodes A and B that we need to burn. So for which, what we are doing, we are checking what is their ancestor. So as here we have checked that who is the ancestor for, who is the common ancestor for your 4 and 5, right? Which was 3. So we have put the fire on 3. Let's say If our A was 4 and if our B was 2, right? Let's just suppose, let's just see what we would do in that case if your A is 4 and B is 2. So you can see your A is here and your B is here. You need to put fire at some place at that place at which, so here you can see you need to put fire at some place which would be ancestor of both 2 as well as 4. So we need to put fire on some common ancestor. Here if you will see who is the common ancestor. So is 3 is the common ancestor? Do 2 and 4 comes inside 3? No. Then we will check for 1. Is your 4 and 2 comes in the subtree of 1? So yes, they do. So if we will put fire on 1, then 2 and 4 both will get burned, as well as all subtrees of 1 would get burned. So if we are putting fire on 1, 1 would get burned, 2 would get burned, 3, 4, 5 would get burned. So all the 4, 5 nodes would get burned in that particular case, right? So here, if you are able to observe, what we are basically doing, we are finding the common ancestor, right? We are finding the lowest common ancestor of both the nodes, and we need to put fire at that. Now here comes the first task, that how you will find the lowest common ancestor. So for that, what you can do, so as here you would be getting q number of queries. So it's not a wise thing to find common ancestors for every query, right? just by just by making calls every time. So what you can do, for every node you can store their ancestors. So for let's say for 1, which all are the ancestors of 1? So let's say only 0 is the ancestor of 1. For 2, who all are the ancestors of 2? So 1 and let's say 0 are the ancestor of 2, because as we know some root node is always our ancestor. So for 3, who is the ancestor of 3? So let's say we are having a node 1 and 0, ancestor of 3. Who is the ancestor? So here we can say, let's say 3 and 1 and 0 are the ancestor of 4. And in case of 5, what we can find, that who all are the ancestors? So 3, 1 and 0 are the ancestors of 5. Now what you can do, as soon as you are getting two numbers, for example, if you have got a is equals to 4 and b is equals to 2, what is the first thing that you are going to do? You will find the lowest common ancestor. So for 2 and 4, what is the lowest common ancestor? So here you can see 1 is also a common ancestor of 2 and 4, as well as 0 is also the common ancestor of 2 and 4. But we will not gonna consider 0. Reason being, 0 is not lowest. Before that 1 is already there to be your lowest common ancestor. It is lowest. So we will always choose the one which we have stored first. That would be your lowest common ancestor, right? Now, from this, you will know that, okay, I have 1 as my LCA, lowest common ancestor. After that, what is your next thing that you have to figure out? Next thing is, you should know how many childs. Next thing is, you should know how many descendants are there for that particular ancestor. So for 1, you should know how many descendants are there. So for this particular thing, what you can do, you can count your descendants. So for 1, there are 4 descendants, 2, 3, 5, 4, right? So there are, for 1, there are 4 descendants and 1 itself. So total nodes burned would be 5, right? But it's not a wise thing to find the number of descendants every time for every query, because you would have to do repetitive calculation. For example, when you are finding the descendants of 3, you will find, okay, there are two descendants of 3. But now, when you have to find the descendants of 1, for that also you will be again finding the descendants of 3, right? So it's a wise thing to store your descendants, number of descendants, right? So here you have stored your common ancestors. Similarly, you can store your number of descendants for every node. So here, one, one is having 4 descendants, 2 is having 0 descendants, 3 is having 2 descendants, 5 is having 4 descendants, and let's say 4 is having 0 descendants. Sorry, 5 is having 0 descendants, right? So this is the case. Now, as soon as you will get that 1 is my LCA, lowest common ancestor, I can see how many descendants it have. It is having 4 descendants, as well as it would burn itself. So total number of nodes burnt would be 5. Simple. So guys, here what you need to do is, first is you need to store all the ancestors for all the nodes. Second is you need to store all the descendants for all the nodes. Second is you have to store number of descendants for all the nodes. Then what you are gonna do? Firstly, you will find the lowest common ancestor, and after that, for that LCA, you can find the number of descendants, and it and 1 itself would be burnt. So total would be number of descendants plus 1 would be your answer. That is total number of nodes burnt, right? So let's just see how you can implement this particular approach. So just to save some time, I have already implemented the solution for you. Now let's just go through this particular solution, that what we are going to do here. So firstly, I have just taken the data input from the user, right? Then after that, let's see what we have done. So here we have the solve function. So firstly, you are having this main function in which we are taking the input, and first line of the input would be a number of test cases. So we have taken test cases in the input, and for every test case you will get a new tree. So that's why we have called our solve function, right, for every test case. Now let's see what this solve function would do. So in this solve function, we would take the first line that would be telling your number of nodes as well as number of queries. That would be n and q. So here we have stored n and q, right? Next thing is that we need to store all the edges, that 2 and 3 are having an edge, right? After that, we have taken a variable size. It would be storing the number of descendants. That is basically size of your
नेट खत्म हुआ मेरे जाओ खिलो
subtree, right? We are taking it of size n plus 1.
नेट खत्म
Why
हुआ
n plus 1? Because here there would be n nodes. So for n nodes, we are taking the array of size n plus 1. Initially, we are filling it as 1 because at least every node would be a subtree of itself. So size of one node would be at least 1. That's why initially we are storing 1 in the whole array of size. The next thing we are storing is depth. Why we are storing depth when we have stored size? So just storing depth would help us to check that which particular node is more nearer to your lowest common ancestor, and accordingly we can find your lowest common ancestor if we know the depth. So if one node is having more depth and another one is having lower depth, so that means the node with the lower depth is nearer to your So that means the node with the more depth is much nearer to your lowest common ancestor than the node having lower depth, because that would be lower in the hierarchy, right? So depth would help us to reach to your um, lowest common ancestor quickly. Now here we are storing up. What does up means? Up means the ancestors. As we have thought earlier, As we have thought earlier that for every node we would store its ancestors. So here in the up array we would be storing its ancestors, right? Now what we are doing, that for every edge, for every ith edge we are storing an array. Why we are storing an array? Because as we know, all the nodes would be having bidirectional edges. So by bidirectional edges we mean that you can go from x to y as well as from y to x. So that's why we need this array to store that for this particular node x we have a path till y, right? Instead of taking here array of arrays like 2D array, you can take a map or an object also. That is also fine. Now here we have filled our ancestors array with 0 initially. So here for ith node, let's say we are assuming that there would be at max 20 ancestors, and initially we are storing 0 in the whole array of ancestors. So initially we are saying for every node its ancestor is 0. Moving forward, we are traversing Moving forward, we are traversing through all your n minus 1 edges. That is basically your tree that is given, in which it is given that there is a edge from x to y and y to x. So we will take that input that okay, there is a node x and there is another node y. There is a edge between x and y. So what we are doing, we are just pushing that in edge of x we are pushing y, and in edge of y we are pushing x. That means there is a path from x to y as well as there is a path from y to x. As we know, the edges are bidirectional, right? So after this loop we would have stored all the edges of your tree. So just by storing all the edges of your tree we have created your tree. Now moving forward, we will call the DFS function. What this DFS function would do, in this DFS function, we are passing your ancestor, your edges array, your depth array, ancestors array, and your size array, right? And this DFS function would help us to fill all these arrays. For example, it would help us to find the depth of all the nodes. As I have told you, we won't do this work again and again. We will once store the depths of all the nodes. We will store all the ancestors of all the nodes only once, and similarly we would store the size of all these trees only once, right? So let's just see how this DFS function works and how it would help you to store the values in all these arrays. So here it is your DFS function. What it is doing is, so there is we have passed the root. So for root, so in this DFS function we have taken root, parent of the current node, your edge array, your depth array in which we would be storing the depths, your up array which means your ancestors array in which we would be storing all the ancestors of all the nodes, and your size array in which we would be storing the size of the trees for every node, right? Here what we are doing, so for root node we are saying that traverse through its children, and for every child you have to do some steps. What you need to do for every child of root, so firstly you need to check child is not equals to parents. If child is equals to parents, if child is equals to parent, that means we are considering that particular node again. For example, if 4 is a child to node 3, so we have came from 3 to 4. Now as the nodes Now, as the edges are bidirectional, so there would be an edge from 4 to 3 as well. But we don't need to explore that particular edge as we have already explored 3 to 4. So we want to go again from 4 to 3, right? Now we will say the depth of child would be equals to depth of your root plus 1. So as your child would be on the next level of your root, right? If root's level is 1, your child's level would be 2. So what we are doing, we are just increasing the child's depth by 1 of its root, as child would be on the next level of its root. Next thing what we are doing is, so here we are storing the ancestor of your child. So here we are storing the 0th ancestor of your child is root. So that is very basic. We know that the 0th ancestor of your child would be its just root, or you can say its parent, right? After that, what we are doing, we are saying that okay, now get me the now get me all the ancestors of our child. How we can get all the ancestors of our child? So let me show this on your screen. So let me show this to you. So if you are having if you are having a tree something like this, 1, 2, 3, let's say 4 and 5. So and if we are storing the ancestors, then initially we would come to node 1, and let's say it is 0th ancestor, first ancestor, second ancestor, third ancestor, and we are just saying that at max we can have 20 ancestors like this. So here, firstly we would store for node 1, then we would store for node 2, and similarly we would store for all the nodes, node 3, 4 and 5. So here, when we will come to 1, we know that who is its ancestor? Is its ancestor is 0, so we will just store 0 here, right? Now, when as we are exploring the child of root, right? So when we will come to 2, the child of our current root, so we will store that ancestor of 2, the direct ancestor of 2 is 1 only, which is its root. So here we will store its 0th ancestor is 1, right? And now we have to store that who is its first ancestor. First ancestor means who is the ancestor of your ancestor. Okay. So here you can see how we can find that. So firstly we would say, okay, my ancestor was in the just last box, right? Just last column. So if your these columns are J, and if you are currently at this jth column, then you can say that my ancestor is at J minus 1th column, right? Right? And what is its row number where your ancestor is lying right now? So your ancestor is lying at this particular row, which is equals to you, right? So you can see your current child, like if we are calling it as ancestor array, so then your current child and J minus 1 column is giving you where your ancestor lies. This is your ancestor, right? Now what you need to find is, you need to find the ancestor of your ancestor, right? You need to find the ancestor of your ancestor. And from this case, you can see where your ancestor's ancestor is lying. So one's ancestor, this is one, where its ancestor is lying? It's lying at this position. So you can see from this, we have just got our current ancestor. So we are the child, we are 2. From this particular thing, we have got our ancestor, that is 1. Now we want to find our ancestor's ancestor, right? So if we want to find our next ancestor, that is our ancestor's ancestor, so we can say we need to find one's ancestor. So we can say get me its ancestor, where it would be lying. If our current index, if our current column is J, then it would be lying just one step behind, that is J minus 1. So here you can see this is our current position. We need our first ancestor, and our first ancestor, would be the 0th ancestor of your ancestor. For example, if we are talking about the hierarchy in terms of human, So it's just like your grandfather, then your father, and then you. Okay. So for you, your father is at hierarchy 1 and your grandfather is at hierarchy 2. But but if we will talk about your father, or your father, your grandfather is at hierarchy 1, right? So basically, what I'm trying to say is if you are at jth level, if you are finding your jth ancestor, if you are if you are finding your jth ancestor, if you are finding your jth ancestor, then that would be j minus 1th ancestor of your ancestor, right? So here so here you can see, if we want to find the second ancestor of you, so it would be your grandfather. So it would be your grandfather, right? But for your father, it would be his first ancestor, right? So we are just basically saying your jth ancestor would be j minus 1th ancestor of your ancestor. Simple. So here, firstly, so here, firstly, we are finding that who is your ancestor just by doing that who lies on your j minus 1. That would be your ancestor. Then next thing is, so firstly, we are finding that who is your ancestor. So initially, it would be your parent that we have stored at index 0, right? After that, once we have got who is your parent, that is in this case 1, then we are saying that for this particular one, who is its ancestor. So how we will get its ancestor? But just by doing j minus 1, because we know that if we are trying to find our jth ancestor, it would be j minus 1th ancestor of our parent, right? So here you can find it that your j here is 1, but would be your j minus 1? It would be 0. So in your ancestors array, for 1 at 0th index, who is the ancestor? So for 1 at 0th index, it is 0. So you can say my second ancestor is 0. And similarly, you can move forward for 3. For 3, you will just see who is your parent. Your parent is 1. Cool. Then you would say, okay, I want to find my first ancestor. My 0th ancestor is my parent, 1. Who is my first ancestor? So firstly, you will see who is your parent. So your parent is 1. You want to find your first ancestor. So you need to find the 0th ancestor of your parent. So who is 0th ancestor of 1? So from here you can see it was 0. So your first ancestor would be 0 only. Simple. Now let's talk in terms of 4. So when we will come to 4, who is the parent for 4? 3. So we can say 0th ancestor of 4 is 3. Now, who are the ancestor? Who would be who would be your first ancestor? So your first ancestor would be your parents' 0th ancestor. So you can say, get me, if I want my first ancestor, get me 3's 0th ancestor. So firstly, from this you will find that who is your ancestor, that is in your current row at j minus 1, who is there? It is 3, your parent. We want our first ancestor, so we can say, get me my parents' 0th ancestor. So ancestor of 3 at 0th. So 0th ancestor of 3 would be, here you can see it is 1. So we can say our first ancestor is 1. Now, if we want to find our second ancestor, who is our second ancestor? So our recent ancestor would be our second ancestor. So who is our recent ancestor? You can see if our j here is equals to 2, if j is equals to 2, so who is your recent ancestor at j minus 1? It would be 1, right? And we can say 1. Who is your ancestor? So if I want to find the second ancestor, I can always ask for your first ancestor. So as you know, initially we have filled everything as 0 in your array. So we were just basically saying 0 would be the ancestor of all the nodes initially. So, so from this, the first ancestor of 1 you can find here, it would be 0. So we can say our second ancestor would be 0. And same thing we are going to do with 5. We will store 5's parent, that is 3. Then we will ask that who is 3's ancestor. So 3's ancestor is 1, that we will store here. Then we are going to ask who is 1's ancestor. So 1's ancestor is 0, that we are going to store here. And everything else would remain 0, 0. Right? So here we have already stored that who is the ancestor of who. Right? So same thing we are going to do in the code. Let's just see how. So as you know, firstly we have stored our 0th ancestor, which is our root. That means just our parent. Right? After that, next thing that we are going to do is we are traversing through all the 20 possible ancestors that you can have. And 20 is just a constant number that we have taken. Instead of 20, you could have n also, that is the number of nodes, because at max you can have number of nodes ancestors, right? And here what we are doing, that your ancestor, your jth ancestor would be equals to, firstly find your ancestor. So we are finding your ancestor just by doing this. Your j minus 1th ancestor would be this, who would be lying in your current row child at j minus 1th index. Now you want to find jth ancestor. So we are just saying for your j minus 1th ancestor, find its j minus 1th ancestor, right? So this is how you would get his ancestor, right? So by this you can fill up your array of ancestors. After that, once you are done, once you have filled the ancestors of your current child, then what you will do, you will call this DFS again, and now you are passing root as your current child. Okay, so now the current child would become the root and its parent would become your current root. So right now, if your parent was earlier 2 and your child was 3, now the root would become 3 and its parent would become 2. Okay, and everything we are passing same, everything else. And at the end, what you are gonna do, what you will say that size of your root would be equals to size of your current root plus size of your child. So current sub size of your current tree of starting from root would be equals to size of your tree of your child. So basically, if you are at the root, your left child is getting a tree of, let's say, size 3, and your right child is getting a tree of size 4. So 3 plus 4 would give you 7, and you yourself was starting 1 initially, right? Because we have seen that every node would be at least of size 1. So 3 plus 4, 7, plus 1, 8 would give you the total size of your tree, that is 8, right? So by using this DFS function, we have achieved, or you can say stored, all the values of your ancestors, as well as your depth for all the nodes, as well as the size of trees for all the nodes. Let's see what we are going to do after this. So once we would be having all these values, we will just start taking your queries. Okay, so in queries, what you are getting, first you are getting that there would be a node x, next is you are getting that there would be a node y, and we are saying for this node x and y we need to get its LCA. Okay, and how we would be getting LCA, let's just see. For this we are passing our depth array and our ancestors array for get LCA. So in the implementation of get LCA, what we are doing, we are checking if depth of node A is smaller than depth of node B. If that is true, that that depth of node A is smaller, then we would swap them. Why we would swap them? Because we always want depth of node A greater than depth of node B. Okay, we are always considering the case in which depth of node A would always be greater than depth of node B. It would just make it easier for us to judge. So here, the next thing that we are gonna do is we will iterate through all the ancestors of A. After finding the difference between the depth of both, we will just try to find all the ancestors of your that node which is having more depth, because it would be at the more lower level in the hierarchy. So we are just going through all its ancestors. So as you know the that we only want the lowest common as you know we only want the lowest common ancestor. So here what we are trying to do is, firstly we are ignoring all the zeros at the end, because we have taken a 20 size array, right, for all the ancestors. So it's not possible that every time you would be having 20 ancestors for every node. So we are just ignoring all the zeros at the end, and if there would be some number, if an ancestor would be some number apart from 0, that would be stored into A, right? Now at the end, after this for loop, in A, you would be having your lowest ancestor, right? Just your parent. So here you are checking, is your parent, is your lowest ancestor is equals to your B? If your A is equals to your B, if that's the case, that means both the nodes are equal, right? If that's the case, then both the nodes are equal, and you can just return A, that A is my lowest common ancestor. So it may happen that your both the nodes are the same node. For example, the case of query 2 comma 2, in which you were having both the nodes were same, only 2, right? So in that particular case, you would be your in that particular case you would be your lowest common ancestor, and you can return A. Otherwise, what we will do, otherwise we otherwise what we will do, we will again start from the end, and we will move forward until we will find our lowest common ancestor. So until we are not finding our lowest common ancestor, until your common ancestors are not equal, we are just keep updating A and B. At the end, we will have the lowest common ancestor, and then we can return our lowest common ancestor from this particular function. So in LCA, we will get our lowest common ancestor, and as we have stored the sizes of all the trees, so here you can just return the size of this particular LCA node of the lowest common ancestor, right? So that would be the size of your tree that you need to burn. Cool. So guys, I hope this particular explanation does make sense to you, and you would be able to solve this particular problem on your own. So thank you. Take care.